Hi, and welcome to section 4.2, modeling with linear functions. Modeling is code word for story problems, so we're going to basically just do 4 story problems today. I think it's 4. All right. Oh, I'm scrolling like crazy. Hang on. Okay, here we go. So what we want to do is we want to make sure that we can read linear word problems and get out the important information to come up with a linear function for the description. There's some strategies that can help you. Number 1 is that you need to really carefully read the problem and highlight the important information. You need to then define your variables, including their units that represent the input to the function and the output. As you're reading through, try to identify the slope or the constant rate of change. Lots of times there's keywords to identify the slope, such as per or for each, that indicate a rate. You need to identify the y-intercept. It's usually a fixed amount. Sometimes it's initial value. Sometimes they don't give you the y-intercept and you have to use another data point for the y-intercept, but sometimes they do. You could try sketching a graph. Sometimes that helps. Then you create the function and evaluate as necessary. Let's do some examples. All right, here we go. Michael is selling coupon books. At the end of each week, Michael gets $10 for that week, plus $3 for each, that's a keyword, coupon book sold in cash. How many books will Michael have to sell in a week if he wanted a Super Soaker that cost $29.99? All right, so let's go ahead and read this again and identify some important information. So Michael is selling coupon books. At the end of each week, Michael gets $10 for the week, okay, plus $3 for each coupon book, okay, in cash. Now, let's ignore the last bit, okay, until the end, because we don't have our function yet. We need to answer a question, but we don't have our function yet. All right, so let's see if we can figure this out. All right, what is our input variable? Input. And what is our output? Well, we're going to put in is going to be number of coupon books sold. The number of books he sells tells you how much money he makes per week. So the output is dollars earned total per week. Okay, so my input for Michael's business here is going to be how many coupon books he sells, and that's going to tell me how much money he gets at the end of the week. All right, well, let's write this function as, I don't know, let's call it money as a function of coupon books, M of C. How about that? M of C. So we're going to do C is the number of coupon books, and M of C is going to be the total money he gets at the end of the week. Well, he gets $10 no matter what, right? Even if he doesn't sell any coupon books. Plus, he gets $3 per coupon book, or for each coupon book. So if he sold 1, he'd get $3. If he sold 2, he'd get 6. If he sold 3, he'd get 9. So I'm going to multiply that 3 by C. And there is my nice linear function that represents this situation. If you wanted to rewrite it in slope-intercept form, that's fine. M of C equals 3C plus 10. Those are the same. All right, so let's go ahead and see if we can answer this question. How many books will Michael have to sell in a week if he wanted a Super Soaker that cost $29.99? Well, one thing that can help you, you're going to put the $29.99 in somewhere. We just have to decide if we put it in for C or M of C. One way that helps me figure this out is I look at the units. The units are in dollars, so that tells me that I need to put this in for the output, M of C, because that unit is dollars. If I was asking about number of coupon books, I would put that in for C because that's number of coupon books. So I'm going to put $29.99 in for M of C, and I'm going to solve 3C plus 10. All right, we're going to subtract 10 from each side. $19.99 equals 3C, divide by 3. I'm going to have to pull my calculator out here because I don't think I can do that in my head. $19.99 divided by 3 equals, I'm going to write this down, 6.6633, repeating. All right, now I've been telling you up till this point, you can't use decimals if you're going to round. However, story problems are the exception to that. You can't sell 6.6633 coupon books, right? That's impossible. You can sell 6 or you can sell 7, right? So you need to look at this answer and think, is the answer 6 coupon books or is it 7? Well, if he sells 6, we can plug it back in really quick. If he sells 6, he'll get $18 plus 10 more is $28. That's not enough, right? So that one's not going to work. If he sells 7, he'll get $21 for the coupon books plus $10 more. He's going to be at $31, and he will have enough to buy his Super Soaker. All right, so rounding does come into play when you're solving word problems. All right, let's try another one. You take your car to a mechanic because there is something wrong with your brakes. The mechanic charges $45 just to look at it and tells you that you need new brake pads. Parts cost $90 and the mechanic charges $75 per hour to actually work on your vehicle. You get a bill for $300. How long did that mechanic work on your car? There's a lot of stuff going on here. Let's read it again and sort of highlight important information. All right, we took the car to the mechanic because there's something wrong. The mechanic charged $45 just to look at it. That's a one-time fee, okay? So that's a constant one-time fee. And he tells you need new brake pads. The parts cost $90, okay? That's for all the parts, so that's, again, another one-time sort of fee. You're going to pay $90 for those brake pads. The next thing, it says he charges $75 per hour. All right, so that's a rate, okay? And finally, the formal bill is $300. Final bill is $300. All right, so let's see if we can figure this out. What is our input into this? And what is our output? Well, the input is going to be, it's $75 per hour. The input is going to be the number of hours the mechanic has to work on my car. The number of hours worked on the car. If he's fast, it's going to be less hours. If he's slow, it's going to be more. If it's hard, it's going to be more. The output is going to be the total charge of the bill, right? Total bill. All right, so let's do input of hours. Let's make that H. Let's make total bill, and this is in dollars. I just told you guys to always use units, and then I didn't use units. Total bill, let's make that B. So our function is going to be B of H. All right. So let's look at, see if we can build that function. Well, I only have one rate, $75 per hour. So 75H. That's going to be for each hour I have to pay $75 plus I have to pay the $90 parts and the $45 just to look at it. 90 plus 45 is 135. So there's my linear function that represents my bill as a function of the number of hours he worked on it. Now I get to finally ask my question here. Your bill is for $300. How long did the mechanic work on your car? Again, I'm going to look at the units. It's not hours, right? I want to know hours. It's putting it in for dollars. So I'm going to put in 300 for my B of H and solve. Subtract 135 from each side. That's 100. No, I did that wrong. 300 minus 135 equals 165 equals 75H. Divide each side by 75. Divide by 75. And I get H equals 2.2 hours. Now, be careful. That is not 2 hours and 20 minutes, right? 0.2 hours is not 20 minutes. How would you figure out what that was in terms of hours and minutes, right? Well, you need to take 0.2 of 60 to figure out the minutes because there's 60 minutes in an hour. So that's 12 minutes. So you could either write 2.2 hours, that's probably fine, or you could write 2 hours and 12 minutes. That's how long he worked. All right, let's try one more problem. So this one's a little bit different. I gave you the function in this one. A can of frozen orange juice is taken from a freezer and gradually warmed. The equation T of x equals 3x minus 6 gives the temperature in degrees Celsius. So it gives the temperature in degrees Celsius of the orange juice x minutes after it is removed from the freezer. All right, so let's start asking these questions. It says, what is the vertical intercept? Well, we know how to do that. Here's my function, right? Here's my function. And I know that -6 represents my b value, right? B is equal to -6. So I know my vertical intercept has to be over 0 down -6. But what does that represent in the context of the problem? Sometimes it helps me to remember my units. So remember, my units on the input are minutes. So 0 minutes gives me an output of -6 degrees Celsius. 0 minutes gives me an output of negative 6 degrees Celsius. So that means when I take it out, when the orange juice is taken out at time 0, it's taken out of the freezer, it is negative 6 degrees Celsius. All right, well, let's look again. What is the slope? What are the units on slope, and what does it represent in the context of the problem? I can read the slope right from the equation. It's 3, and I'm going to write 3 to 1. The slope is 3 to 1. What are the units on slope? Now remember, units on slope are units on output divided by units on input, rise over run. So 3 degrees Celsius per minute. 3 degrees Celsius per minute. Okay, so what does that represent in the context of the problem? It helps me when I say the units, 3 degrees Celsius per minute. 3 degrees Celsius per each minute. So that means the OJ is warming 3 degrees Celsius per minute. And what is the horizontal intercept? What does that represent in the context of the problem? This is a little bit trickier one. What is the horizontal intercept? That would be when the output is equal to 0. So we would need to solve t of x equal to 0. So 0 equals 3x minus 6. Solve this for minutes. 6 equals 3x. Divide by 3. X equals 2. And remember, x units are minutes. 2 minutes. So this is the point over 2 minutes up 0 degrees Celsius. So what does it represent in the context of the problem? After 2 minutes, the orange juice is at 0 degrees Celsius. After 2 minutes, the orange juice is at 0 degrees Celsius. All right. All right, here's our last example for section 4.2. So let's assume the number of SUVs sold in the United States represents a linear model. In 1990, about 1.1 million SUVs were sold, and in 1992, about 1.8 million were sold. All right, the first question asks, what is the average number of SUVs sold per year in the United States? All right, so this is an average rate of change problem. So I'm going to do 1.8 million minus 1.1 million over 1992 minus 1990. So this is million SUVs over years. And let's see here, 1.8 minus 1.1, I should probably do that in my head, but I think it's 0.7. 1.8 minus 1.1 equals 0.7 million SUVs over 2 years, which is 0.35 million SUVs per year. You could leave it like that, or you could write it out as 0.35 million, which is going to be 350,000 SUVs per year, but it's okay to leave it as million SUVs per year. All right, so now we're going to let t equals 0 represent 1990. Find an equation that can predict the number of SUVs sold in the U.S. t years after 1990. Well, if we already have our slope, right? We know that an average rate of change is our slope, so we already have our slope. And our y-intercept is telling us it's 1990. Well, in 1990, it was 1.1 million SUVs, so we have our b value. We have our m value from our slope and our b value from the problem. So we can write an equation right now. So we'll maybe call it S of t, number of SUVs per year. It's going to be 0.35t plus 1.1, right? So S of t is equal to the number number of SUVs in millions. We'll write that. Sold in millions. And t is equal years since 1990. means 1990 is t equal to 0. All right, so use your model to predict the number of SUVs sold in the year 2000. Well, the first thing we need to do is if t is 0 in 1990, then our t value for 2000 is going to be 10 years after 1990. So if t is 10, we're going to find s of 10, right? Plugging in for years. 0.35 times 10 plus 1.1. All right, so 10 times 0.35 is 3.5 plus 1.1 equals 4.6 million SUVs. All right, in what year will the US have sold 2 million SUVs? So in this first one, I was plugging in for T. I was plugging in for the input. In this one, I'm plugging in for the output. The units are million SUVs. So I want to set 2 equal to my S of T. All right, let's solve this guy. Minus 1.1 from each side. 0.9 equals 0.35t. Divide by 0.35. And I get t equals 2.57 ... but I'm going to round. So if t equals 0 is 1990, then t equals 2 is 1992, and a little bit more means during 1992, right? Halfway through 1992. All right, that's it for modeling with linear equations. If you need any help, be sure to contact me.